Okay, so a few things to fill in here. If the values of a function are the same for each given interval of the domain, the function is said to be periodic. The length of the interval that is repeated is called the period. So what we're looking at is what we're going to see is that in these functions, we're going to see the graph is just going to repeat over and over and over and over again, right? So I went ahead and filled in these values from the unit circle, right? So if you just have finished, you may not have time to do that, but you should have 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. You should already see some repetition there, right? So these numbers here are going to go on our x-axis. I'm going to explain just a little bit further exactly what this is. So, like if I have 0 right here, and if I make this pi over 2, it seems a little odd to do 0, pi over 2, pi, 3 pi over 2, 2 pi. Those seem sort of unrelated, but they are not. Because what you're doing here, if this first little tick mark is pi over 2, the second one is 2 pi over 2. The next one is 3 pi over 2, and the last one would be 4 pi over 2. However, some of these reduce, right? 2 pi over 2 is just pi, and 4 pi over 2 is 2 pi. And then you'll have the opposite thing happening here on the negative side. And so since my lowest number here is negative 1 and my highest number is positive 1, I just want to make this on the y-axis, I'll make that negative 1. I'll make this positive 1. So if I graph my points, I've got 0, 1, 0, negative 1. 0, 1, 0, negative 1, 0. There, so. And so you have already done some of this, so hopefully you knew how to draw this in. But it looks like a zigzag. Is it going to be a zigzag with straight lines? No. It is not. If we wanted to fill in some extra points, like pi over, if we split this into 3 little pieces right here, this would be pi over 6, and this would be 2 pi over 6, which would be pi over 3. Like if we put those values there, pi over 6 is 1/2, right? And then pi over 3 is square root of 3 over 2, which is like 0.8 or something, I think. So that would be like up here. So like if we filled in all of the values, you would be able to see that it's going to be a curve and not just a straight line. So when you draw this in, it's not, you don't have to have it perfect, but you do want to have curvy lines. So if we graph sine using that unit circle, what happens is the values just keep repeating over. Like if you think about the circle, you just keep going around and around and around, so you keep hitting those same values. When we graph that on a linear graph here, where instead of like circling around, where our radian values are just increasing and keep increasing, we're going to see this repeat in this wavy graph right here, which is where we start going from triangles, right? We went from triangles, which is what we did in Unit 5. Then we went to the unit circle, so we took those triangles and put them on a circle. Now we're using that circle. That circle's like we're spinning around as we go around it, around and around and around, and we're translating it to this graph, right? So what happens here is we really get away from triangles whenever we are talking about trig. One of my Math 1 kids was asking me about this the other day. I told them that trig is easy until you quit using triangles with trig. Even though most students do pretty good with these graphs. It's the next part that they have a little bit of trouble with. So this is all related. This is why something like these problems, and we're going to look at it some, can be used to model anything that repeats itself over and over and over again. So like the hours of daylight that you have every day are going to repeat using a sine function. So it has nothing to do with triangles, or it doesn't seem to, but trig can be used to model that behavior of the hours of daylight. So it's kind of interesting how things like this can apply in what seem to be like unrelated situations. That's one of the things I think makes math so cool is like how all of these pieces of things sort of fit together and can be like used in different ways. It's not just like triangles only apply in this. It can be extended and applied in what seems to be a totally unrelated sort of situation. And I don't even begin to understand like all of it and how it all fits together. But e's are sort of the same way. Like e to the x, when we did exponentials, they show up in crazy places that don't seem to be related to exponential growth. It's pretty cool. All right, so the length of the period is how long it takes for your values to start repeating. So think about the unit circle, right? On your unit circle, and that's what we're graphing here, is just straight sine of x. On the unit circle, those sine values, you're going to go all the way around one time, and then after that, it's going to be the same numbers over and over, right? So how long does it take for that to happen? 2 pi, one full rotation, right? So our period is 2 pi. And if you look at, if I highlight on this graph right here, that interval from 0 to 2 pi, if you kind of think, if I made a stamp that was just this section right here, I could graph the whole thing just by using that stamp, like a stamp, and then put the next stamp down. It's just this over and over and over again. All right, our domain for this, domain are your possible x values. It is all real numbers. So all real numbers, or you can do negative infinity to infinity. There is no number that you cannot plug in. You can plug in 0, you can plug in negatives, you can plug in positives, decimals, fractions, anything can be plugged into sine of x. Range, however, is restricted. Range is your y values. Almost. Caleb said -1 less than x less than 1. He is almost right. It needs to be or equal to, because at that, like those maximum and minimum points, it actually equals 1. So you want to put it or equal to. So, or we could write it with interval notation, -1 to 1. Okay, questions on that? So you need to know in general what the sine graph looks like, because we are, after we finish this, we're going to look at transformations. And so one of the key things about the sine graph here is I like to remember that y-intercept right there is going to be at 0. Because we're getting ready to graph cosine. Some of you have already graphed cosine. It doesn't look much different, does it? It looks a lot the same. Yes. So, when we graph cosine, you should, in this chart here, have 1, 0, -1, 0. 1, 0, -1, 0. 1. there. So you can see the pattern is very similar. We're going to label our x-axis the same as we did for the other. Okay, and so when we graph these points, our graph will look like this. So from afar, like these graphs look basically the same, right? They're just that same wavy curve. Our main difference right here is that our y-intercept on this one is at that maximum point, right? It's at 1. So it's, a lot of times you'll hear me call it the starting point. That's really not the best mathematical language for me to use. I should call it the y-intercept, but this graph, that y-intercept is at a maximum point. It's at that 1, and then it goes down from there. Whereas sine, your starting point or your y-intercept there is at 0. But the pattern is going to continue the same. All right. We're going to see the same thing here. Period for this is the same. It's going to be 2 pi. Domain is also all real numbers. Our range is also the same, -1 less than or equal to y less than or equal to 1. Oh, I messed up on the last one. What did I do wrong on range? It should be y instead of an x. Right there, let me fix that. We don't put y's in stuff like that often. Okay, so all this is really doing is we're taking those values from the unit circle and we're translating them to a graph. So our trig, so whenever, that is why whenever you see a trig graph, it repeats over and over and over, because as you spin around that unit circle, you get those same numbers over and over and over again. So like as far as what you need to know about this, you need to know the general shape of these. You need to know those y-intercepts and the period and those sort of things. But this is huge and also seems very small, right? It seems like kind of insignificant, but it is really important. It's kind of like one of the main reasons we even look at that unit circle is so we understand that like as you're spinning around and around and around, those values keep repeating over and over and over again. I actually numbered that wrong. These notes today, the second part of the notes are 6.2b. So let me pass those out. Oh, I did not staple or you guys can live without the staple. Give me a second here. That copier in there will staple, but it runs out of staples all the time. Make sure you don't realize it. Okay, these notes are not stapled, so you need 2 pages. Let me just get them out. Each individual person will take longer, but it will make sure that everybody gets what you're supposed to get. Question is this going to take me longer, or would it be quicker for me to staple? That's the question.
more letters than there are numbers. There's 3 numbers and 4 letters. My bad.
I'm sure appreciate it. Yeah, just go throw it. I got you. Throw it. Hit him. I'll throw the darn thing. No, you just wreck me. Let's see how that works. Rex and all.
I've not been around like that. I like Hank.
I think the next one.
Do it again, I wasn't looking.
So then, after alligator again, you just go shake your hand before else we get called.
Yeah, they're not very good, are they? Okay. All right. Okay. Right there. All right. Okay. All right. So, transformations to sine and cosine. I also think it is so cool in math how it does not matter if you have a quadratic or a trig function or an exponential or something to the 5th power. Our rules for transformations are still going to apply. With trig, some of them will have a little bit different name, but they still apply. So on some of these, you'll see that I have started off just reviewing some of our transformations. So on this first one, we're going to review translations. Okay, translations are just sliding a graph, sliding it up, sliding it down, sliding it left, sliding it right. Okay, so whenever we slide a graph up, down, left, right, we call that a translation. So let's talk about this. So looking at this one here, Leah, for f of x equals x squared plus 3. What's that plus 3 right there going to do to that graph? Up 3. So this is a quadratic moved up 3 units. And we call that a vertical shift, but if you want to be dramatic, you could call it a leap, maybe. And remember, vertical shifts go the direction that you think they should. They're not on the inside of the parentheses. So if you just put a plus 3 over here at the end, it's just going to shift that up or down, up 3. If you put a minus 3, it would move it down 3. Okay? All right, so for the second one, we've got f of x equals x minus 5 cubed. So, Jeremy, what would this do? Right 5. Good. So it is a cubic, shifted, or moved, right 5 units. And that is a horizontal shift. Okay. So these things are still going to apply for trig functions. If we put a plus 3 on the end, it's going to move that trig function up 3. If we put a minus 5 on the inside of the parentheses, it's going to move it to the right 5. Although there's one thing I actually didn't make you consider with horizontal transformations. I just left it out of transformations. That we do have to pay attention to with trig stuff. So there'll be a little extra something there. All right, so vertical shifts. So if I have something like f of x equals sine x plus 1, that's our general sine function that we just graphed, and it shifts everything up 1. Okay? So whenever we do that, there's an important part of the of trig functions that we need to know how to talk about, and that is called the midline. Okay, the midline is what it sounds like. It's just the line that goes through the middle of the graph, right? So it is the horizontal line through the middle of the graph. Okay, so in our function sine of x that we just graphed, so that graph that we were just looking at, what is our midline there? What line? What equals 0? Y equals 0, which is our x-axis. Right? So a translation up or down is going to move the midline up or down. Right? So a lot of times for these problems, it will not ask you what the vertical shift is. It'll ask you what the midline is. So like, for example, if they asked me for the midline of this problem right here, I would say the midline, I don't know what's happening there, is y equals positive 1. So midline in general is pretty easy to find from the graphs. Most students are pretty good at midline. Okay, questions? All right. Horizontal shifts. All right. For horizontal shifts, if I have something like f of x equals the cosine of x plus pi, this would be the cosine function shifted to the left pi units, right? So for trig functions, horizontal shifts, we call them phase shifts. Okay, they're going to work just like the shifting left and right that we did with our other graphs, but in general, the language is just different. They call it the phase shift. If you think like phases of the moon, right? Phases of the moon repeat over and over again. So phase shift just slides that graph to the left or the right to line it up with a different phase. There is one more thing we have to learn about. I put it at the end for this. This is that thing that I did not make you consider with regular graphs. But we'll get to that in a minute. All right, so expansions and compressions. Those were the more difficult ones, right? And I don't really know why I put these negatives here. I should take them off, and I say that every time I say that every time I print these notes out, and I never do it. The negatives, what do negatives do for graphs? They're going to reflect. Reflections still apply, right? So reflection. So if I did have a negative there, it would reflect it over the y-axis. If I have it. Yeah. So everything is going to work the same with trig. It's just some of it has different names, like things that we will look at. So rather than asking you for vertical shift, they're going to ask you for midline. So you really already know how to do a good portion of this. We just haven't seen what it looks like with trig graphs, other than what you did in Math 3, which may have been kind of minimal because Math 3 has too much in it, and you have to rush through this here. For f of x equals 3 times the absolute value of x. Macy, for this, these are expansions or compressions. What kind of expansion or compression is that first one? Is vertical. And it's vertical because it's on the outside of the parentheses, or in this case, those parentheses are absolute value bars. Is it an expansion or compression? Expansion by a factor of 3. Expansion because it's a big number. When I say big, I mean bigger than 1. So it makes the graph bigger. All right, Lily, what about the next one? I got 0.25 times the absolute value of x. Good. Vertical compression. By a factor of 0.25. So, compression, this is a small number between 0 and 1. It's going to squish that graph down. All right, Caleb, what about the next one? Good. Horizontal compression by what factor? Good. Because everything on the inside of parentheses is sort of backwards, so it's 1 over that number. And Owen, what would we have for the last one? Horizontal expansion. And by what factor? Good. For that one, we're doing 1 over 0.5, which is 1 over 1/2. Dividing fractions is easy as pie. We flip the second and multiply. That's where we get that 2 from. All right, so let's look at how this relates to what we need to know about trig functions. All right, so amplitude is going to be the distance from the midline to a maximum. Or I could say minimum instead if I wanted. Points. Doesn't matter whether it's maximum or minimum there because they should be the same distance away from that midline. So from the midline to the highest point is your amplitude. So amplitude is one of the easiest things to find whenever you're dealing with trig functions. If you have y equals a times sine x, then the absolute value of a is the amplitude of the graph. Okay? So, like for this first example here, my amplitude would just be 3. For the next one, my amplitude would be 1/2. I'm going to add a negative here. What if I have y equals negative 130 sine x? It is going to be still positive 130 because we have those absolute value bars. Amplitude should always be positive. The negative is going to reflect the graph if you have a negative there, but it does not do anything to the amplitude. So amplitude is always positive. Okay? So one thing that we're going to be concerned about finding is the period of the graph. That is something that's important for us to see. If you think of things that we would use this for, we're going to want to know how long it takes for something to repeat, right? So if we are looking at, the number of stray animals that come into a shelter or something, I don't know, but I would think that fluctuates, right? It might be higher at certain times and lower at certain times. It could possibly be modeled by a sine wave, right? Maybe at cold parts of the year, it is higher and then lower in the summer. I don't know. Yeah, I've not worked in a shelter to know the answer to this question. But there's a chance that happens, and we would care about how long it takes for that to start repeating, right? So it's going to be a major thing that we look for. Period, we've already looked at the definition here, but it is the distance on the x-axis that it takes for the values to start repeating. So when we have a number in front of our b right here, or in front of our x, I've called it a b right here, that is going to be a horizontal expansion or compression, right? So if you think about taking that sine graph that you graphed on your paper, an expansion or a compression is a little like an accordion, right? It's either going to spread it out or squish it back in. So our normal period for a sine function is 2 pi. Whenever we put a b right here, it is going to expand or compress that, and it's opposite direction, right? If we put a big number there, it's actually a compression, which squishes it in. It's going to make the period smaller, right? If it is a small number, it's an expansion. So the period is going to be 2 pi divided by b. So if we look at these two examples that I have here, if we want to know the period of the function, we would just do 2 pi divided by the number in front of your x, which is your 5, right? So if I graph sine of 5x, the period would be 2 pi over 5. Let's pull up Desmos real quick, just so you can see what that looks like. I think it's helpful to see it actually. So it is an compression by a factor of 1/5. So, but when we're talking about period, the original period was 2 pi. So that period is compressed by 1/5. So it's like 2 pi times 1/5. So it's a fifth of what it originally was. So when you're asked for period, you want to do 2 pi divided by that b. Okay, so if I graph this, y equals sine x is right here. Y equals sine of 5x is right here. So that red graph, that's my regular. You can see that it's squished in. If I look here, like I can make my axis from 0 to 2 pi. And let's make our pi over 2 or 4. All right, so if you guys are seeing what I'm doing there on Desmos, there'll be some things you can use Desmos on, not all. Right now, we're mostly doing it without. You can just type in pi for pi. So you can, if you change the step over here to pi or pi over 4 or pi over 2 or something, it'll count by pi's instead of counting by 1, 2, 3, 4, 5 there, which will be helpful to you sometimes. So like you can see, this was 1 period on the original function, but it squishes it in and you got lots of periods here. You can see it's actually going to be 1, 2, 3, 4, 5. You have 5, little segments here where you only had 1 on the original. So it's 1/5 of what you had. Okay, let's go back over here. Okay, so if I have cosine of 1/2 x, the period for this one nope, it's 2 pi divided by 1/2. Dividing fractions is easy as pi. Flip the second and multiply, you get 4 pi. When you divide by that fraction, it actually makes the number bigger, right? So this stretches it out, where it used to repeat 2 pi, now it takes 4 pi to repeat. And we could go back and do all of this with degrees, but typically we're going to be using radians for stuff like this whenever we graph. When you get to calculus, there are a lot of things that we do with graphs of sine functions, and everything is in radians. It can be done in degrees, but it's generally, when you get to this point, done in radians more often. Okay. All right, so there is one thing I did not make you consider whenever we were looking at graphs of regular, like of quadratics and cubics and all of the things that we looked at. And you may not have realized, but I never gave you a problem where you had a horizontal compression and a horizontal shift at the same time. And I did that because it's a little bit complicated and I just didn't want to deal with it. I didn't want to further confuse you, and you don't see it very often on problems that are quadratics or cubics. However, we have to consider it for trig functions because it is very common for you to have a period change and a phase shift in a function. All right. So when your period is not 2 pi, it affects your phase shift as well. Okay? So if you see, like we have here, if I switch to highlighter, if you have a number in front of your x and a number out here added or subtracted still inside of the parentheses, you've got a horizontal expansion or compression and a horizontal shift, and that is going to change your phase shift. Essentially, you are like factoring out the b out of this right here. But mostly, if you just remember this rule, you will be okay. If you have a number here in front of your x, it changes your phase shift. All right, so the phase shift of this is going to be c divided by b in the opposite direction. So if we look at some examples here, this asks us to look at period and phase shift. Okay, so for these problems, for this first one, the period would be 2 pi divided by the B number, the number in front of your X, which is 2, right here. So my period would just be pi. The phase shift, I'm going to use a PS here so I don't have to write it out. My phase shift is going to be C divided by B. All right, so the C is the number that's added or subtracted. So that's pi. And then we divide it by B, which is the number in front of our X, which is 2. And since I have a plus sign here, it's going to be to the left. Depending on what worksheet or problems we're doing, sometimes they'll say the phase shift is left pi over 2. Other times they'll just say the phase shift is negative pi over 2. So if it's left, they use a negative. If it's right, they use a positive. It just depends on where the worksheet came from, what they decide to do with that. All right, questions? So if we're looking at the second one here, our period would be 2 pi divided by the number in front of the X, which is 1/3. Dividing fractions is easy as pie. Flip the second and multiply. You're going to get 6 pi for your period. That phase shift, it is going to be the C number divided by the B number, so it would be 9 divided by 1/3. Dividing fractions is easy as pie. Flip the second and multiply. You'll get 27. This would also be to the left. Or you could say negative 27. So, we've covered everything that you need to know. Let's put all of that together. The main 4 things that you're going to be asked for are the period, amplitude, midline, and phase shift. Okay? So, if you have A times sine BX plus C plus D, or if it's cosine, and looks the same form, these are always going to be true. So your period will always be 2 pi divided by that B value. Amplitude will always be the absolute value of A. Your midline will always be Y equals D. And your phase shift will be negative C over B. So out of everything we're doing, like this is what you need to know. If you know this and how it works, this kind of puts everything together in one spot, right? Sometimes you don't have a B or a C or an A, but this sort of puts everything together there. So we won't take a quiz like actually using this for a few more days, but this will not be given to you, but this, like if you are one that likes to write down things at the beginning of the quiz, this would be a good thing to write down because this is tells you how to find all the things that you'll be asked for. All right, so where are we at on time? Got a few minutes. All right, so let's look at a few problems here. So I've got y equals 3 cosine x plus 4. They asked me for period, amplitude, phase shift, and vertical shift. Actually, I'm going to change that. Let's not call it vertical shift. Let's say midline. Okay, this is important to know. You always have an amplitude vertical shift, or not, I'm sorry, not vertical shift, midline. Sometimes you don't have a vertical shift, but even when you don't have a vertical shift, you still have a midline. And period. So you should always have an answer for those. Amplitude, midline, period. There is an answer. You should never put none for that. Sometimes for phase shift, you might say none. There is no phase shift. We're going to say that on this first one. So if we're looking at this problem right here, we don't see any parentheses, which means the parentheses would just be around that X. Right there. So when I'm looking for the period of this function, there is nothing there that changes the period of this function. All right? That B in front of the X, that would change the period. There's nothing there. Right? So what is there is just like a 1. So 2 pi divided by 1 still gives me 2 pi. Right? There are no horizontal stretches or shrinks that would change that period. Our amplitude that comes from this number out front. It would be 3. Our midline, that's going to change with our shifts up and down. So that's this number at the end. Our midline would be y equals 4. We want to put y equals because it's the equation of a line. And then for this one, do we have a phase shift? Is it shifted to the left or right? No, because we don't have any numbers inside of that parentheses there. So our phase shift is none. And phase shift should be the only thing you ever say none for, out of these 4 things that you're looking for. So if we look at the second one, the period for this function, it is 2 pi divided by the number in front of the x. But do we have a number in front of the x? We do not, so that is just 1. So our period does not change, it's just 2 pi. Zena, what would our amplitude be? 1/2, very good. Midline. Does our midline change on this one? No. But we still have one. It is y equals 0. Now, if they ask you for a vertical shift, you might say none, because it has not shifted vertically. But it does still have a midline. So if they ask you for midline, you have one. And this one is going to have a phase shift. Kayla, what would the phase shift be?
3.
Good. What direction? Right or left? Right. In this case, it's just pretty straightforward. It just moves to the right 3 because you don't have a number in front of your x. If we had a number in front of our x, we'd divide by it. In fact, the number we have in front of our x is 1. So if we did 3 over 1, it'd still give us 3. All right. All right, let's see if we can get... Let's skip to 4 because we're about out of time. Okay. All right, so for this one, our period for this graph. Morgan, what would the period be for number 4? 2 pi over 3. Perfect. Okay. Let's see. Valeria, what do you think about amplitude on number 4? Perfect. Okay. There is no number here, but that means there is a 1. So you should always have an amplitude. I'm going to do midline on this. So midline. Joshua, what's the midline going to be? Very good. And we'll put y equals 4. And then our phase shift. Let's see. Lily, what would we get for our phase shift? We get 2. And we do 6 divided by 3, which gives us 2. Is it going to be to the left or to the right? To the right. Okay, do you guys get the idea here. All right, so your assignment tonight is going to be from Delta Math. And let me look and make sure I've got it up there and make sure all is good. Let me show you this real quick as you pack up. For these problems that you get here, for this graph, it's going to ask you to graph 3 cosine of 4x. So our amplitude for this one would be 3. What would the period be? It's going to be pi over 2, all right, because we do 2 pi divided by that 4, so we'd get pi over 2. So if I want to graph this, I'm going to tell, oh, I got to click over here. I'm going to tell that I want this to go up by 1 right here, and then I'm going to do pi over 2 for my axis label. And so pi over 2 is right here. Oh, wait. I can put pi over 2 wherever I want. It really doesn't matter. Then okay. Well, let's see. Actually, I'd put it on the 4th dot right here is what I would do, because that's your period, right? And so cosine is going to start at a maximum point, which is going to be right here, right? Then you would do midline. Then you go to minimum point. It's going to go down to -3 because its amplitude is there. Then back up to here like this. And it's going to draw in that graph. Okay? Always use that 4th dot as whatever your period is, and then it'll graph it correctly. Okay? So you're going to put your period on that 4th tick mark. So 1, 2, 3, 4. And then if it's cosine, you start at a maximum point. What about if it's sine? You start at 0, right? That y-intercept would be 0. So, okay. So let's see what they give us. Let's see if they'll give me a sine. Oh, skip that. Okay. So like for this one, what would my period be? 2 pi over 5. So make that 2 pi over 5. And I would generally, unless the numbers are huge, just always do 1 right there. And then drag this over here to the 4th place. And then whenever you put in your points, sine is going to start at 0. Then you have an amplitude of 7, so the next one you're going to go all the way up to 7. You'll have maximum there at 7. You'll go back here, then you got a minimum at -7, and then back here. We'll graph it for you. Okay, it's not going to give you ones where you have shifts and other stuff involved. It should only have period and amplitude changes, I believe, on the ones that you're going to see there. That should be simple.
Do we have to do all 20?
Yes, they should be pretty quick.